All right, welcome back to part 2 of topic 14, where we're going to do some problems from old public exams that are related to the motor principle, electric motors, and the 3 equations that deal with magnetic fields. Those formulas are F equals BIL sine theta, F equals QVB sine theta, which deals with just charged particles moving in the field, and also dealing with the formula for calculating the strength of the magnetic field from a current carrying conductor, and that is mu I over 2 pi r. All of those formulas are on your formula sheet, your data sheet that you get at the public exam. So let's start and try a few of these problems. All from old publics. So the first one here is we're asked to calculate the magnetic field strength at a point a distance away from a wire. So all we have to do is use the formula that's called Biot's law, or Biot's law, depending on how you want to pronounce it. And it looks like this: B equals mu I over 2 pi r. Okay, so we just had to fill in our values because we're asked for magnetic field strength, so we're asked to find B. So mu, remember, is a given. Okay, in air, it's always 4 pi times 10 to the power of negative 7. That's the value. And the current is given here as 1.5 amps. And we divide this by 2 pi times r. R being the distance away, which is 0.20 meters. Now, be careful that it should be in meters, because if it's not given in meters, you do need to convert it. But in this case, it's already in meters, so it's fine. Now, a real quick tip for this: instead of putting in 4 times pi times 10 to the negative 7, since you've already got a 2 pi on the bottom as well, we can do this. Here's a shortcut. Cross this off. 2 pi goes into 4 pi twice. So that just leaves you with 2 times 10 to the negative 7 on the top, multiplied by 1.5, divided by 0.020. And the answer to that is 1.5 times 10 to the negative 5. And the units for that are Tesla. So the answer to this one would be D. Okay, so that's one of the equations we can use with magnetic fields. The next one also deals with one of the equations. This time it talks about an electron being projected perpendicularly into a magnetic field with a velocity of. As soon as you see the velocity and the fact that it's a single charge, here's the formula. F equals QVB sine theta. Okay, that's the formula we use for a single charge particle moving through a magnetic field. Now we're asked to find the magnitude of the magnetic field. So what we do is we rearrange this formula to be B equals F over QV sine theta. Now all we have to do is plug in our numbers. So the F, the force, is given 1.3 times 10 to the power of negative 13. And on the bottom, all these numbers are given as well. Q, the charge, well, since it's an electron, we know the charge is 1.6 times 10 to the negative 19. That's actually on the formula sheet. It's there as 1.60, but that's fine. The V, that's also given. It's 3.3 times 10 to the power of 7. And sine of the angle, it doesn't mention an angle, but it does say perpendicular. And perpendicular means at a 90-degree angle, so we say sine of 90. And the sine of 90, of course, is just 1. When you do that calculation, you get 0.0246, which rounds off to 2.5 times 10 to the power of negative 2. The answer is B. Okay, so that's the way you have to approach these problems. Let's try the next one. This time, it's the third formula. Okay, the other formula that we were given was this one, and this is again on your formula sheet. F equals BIL sine theta. That's when you have a conductor in a magnetic field, in an external magnetic field. This time there's an angle given, though, angle of 29 degrees, so that's theta. Now the current in the wire, we can just rearrange this equation to say I equals F over BL sine theta. So we plug those numbers in. The force is given 1.2 times 10 to the negative 4. That goes on top. On the bottom we have B, the field strength. Whoops, that's not the force. That's not the force at all. Let's fix that. Let's delete all this here. There we go. The force is actually 9.2 times 10 to the negative 6. So here we go. That's the force. And the field strength is 1.2 times 10 to the negative 4. So that goes on the bottom. The length, L, also goes on the bottom, which is 0.040. And we put the sine of the angle there as well, 29 degrees. And the answer to that, when you do that calculation, is 3.95, which rounds off to 4.0 with 2 significant digits. That one is done. Okay, so we've just done an example then using each of those 3 formulas that are involved with magnetic fields, magnetic field strength. Now, the next question on this page deals with direction. So we've got a proton moving parallel to a straight current-carrying conductor as shown. In which direction will the proton be deflected? Well, this is where your left-hand rules come in. So for a proton, now remember, a proton is a positive charge. But your left-hand rules deal with negatives. So let's use our left-hand rule first. If this were an electron, okay, what you do is left-hand rule says your fingers point in the direction of the magnetic field. So we've got to figure out the direction of the magnetic field first. So the magnetic field around this conductor looks like this. Okay, it's a circular magnetic field. And if my thumb points to the right, my fingers point up the back, down the front, into the screen on the bottom. That's the important part. So on the bottom right here, my magnetic field looks like this. No, sorry, it's X's because it's going into the screen. So I draw some X's here. That's the magnetic field around that conductor. Hold on, no, I got that backwards. I was using the wrong hand. Let's fix that. I had it right the first time when I was doing the dots. Okay, your fingers actually point up the front. I had my thumb pointing the wrong way for some odd reason. Up the front, down the back, which means out of the page on the bottom. All my arrows were in the wrong direction. So that means out of the page or out of the screen would be dots right here. Dot, 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 dot. So there's your magnetic field because of the current in the conductor. Now, whenever you've got a charged particle moving through a magnetic field, you can use your left-hand rule. So if that were an electron, what you could do is you could point your fingers out of the screen, point your thumb in the direction that the proton is traveling, and your palm would point up towards the top of the page. But towards the top of the page, that would be if it were an electron. But it's not an electron, it's a proton. So obviously if an electron would go towards the top of the page, then a proton would go towards the bottom of the page. It's going to be opposite. So essentially you use your left-hand rule, but you switch the direction, okay, because it is a positively charged particle, not a negative. Or, if you want, if you have a positive particle, you can always use your right hand instead. Okay, and that would do the same thing. So if you use your right hand, your thumb pointing in the direction the proton is traveling, your fingers pointing straight at your face, your palm would point downwards. So you still get C that way as well. Okay, so you got 2 choices. You can either use your left hand and reverse the direction for a positive charge, or you can just go ahead and use your right hand, which is going to give you the opposite already. So, your choice. Let's try the next one. This time we're actually asked for the force, so it's F equals BIL sine theta. Okay, we are given the force, or sorry, we are given the field strength, which is 4.6 times 10 to the power of negative 4. We are given the current, 0.56. We're given the length of the wire, 2.1 meters, and we're told it's perpendicular, so that means it's sine of 90. Now, whenever it's 90 degrees, you can leave that part out if you want, because remember, the sine of 90 is 1. So really, that's just 1. Right? That there is 1. So even if you leave it out, it's not going to make any difference to the calculation. But if you put it in there, here's what you get. That equals 5.4 times 10 to the power of negative 4 newtons, which of course is choice B. Okay, done. The next one is a single moving charge. It's an electron. So it's F equals QVB sine theta. And this time it actually asks us to find the angle. So we need to rearrange this equation for angle. Sine theta equals F over QVB. So let's plug those numbers in. The force is given. It's 2.40 times 10 to the power of negative 13. I'm just going to leave the 0 off just for space purposes. There's no charge given, but it does say it's an electron. So if it's an electron, you already know the charge is 1.6 times 10 to the negative 19. The V, the velocity, okay, is 2.00 times 10 to the 6. I'm just going to say 2 times 10 to the 6. And the field strength is 1.50 Tesla. Okay, so you do all that calculation, that equals 0.5. So sine theta is 0.5. So theta is the second function sign, or the inverse sign, of 0.5. In other words, sine of what angle equals 0.5? And the answer to that is 30 degrees. So the answer is D again, 30.0. Okay, so again, not terribly challenging. It's just a matter of using those equations and rearranging them as necessary. This one here, another one where you have to apply that left-hand rule. So you've got three different particles, three particles fired into a magnetic field. So we got P, Q, and R. Now you notice one of them goes straight through. So that tells you, because a charged particle experiences a force, it's actually going to change direction. But Q doesn't change direction at all. Therefore, there's no force on it. Therefore, Q must be neutral. Q has to be neutral because it doesn't change direction. So that means it can't be A, it can't be D, because that says Q is negative or positive. All right, so now we got to figure out, by the two charges that deflect, P and R, which one of those is negative? Well, let's use our left-hand rule. Our left-hand rule says that our fingers point in the direction of the magnetic field, which in this case is into the screen. Your thumb points in the direction that the particle is traveling, which is to the right. And if you do that, your palm points downwards. So that tells you that the charge that deflects downwards, which is charge R, must be the negative particle, because your left-hand rule tells you that. So R is negative. That means the answer then must be C, because choice B says R is positive. And we already know that's not right. So there's your answer. And again, left-hand rule. Those left-hand rules are so important. Make sure you know them. You're going to have probably 2 or 3 questions on your public exam that involve the use of those left-hand rules. That's pretty much a given. Next question. This one here, this is a level 3. This one's a little tougher because there's really no numbers given other than an angle. So what I know is this. F1 equals BIL sine theta, and I'm going to call it theta 1. Whereas F2 is equal to BIL sine theta as well, but I'm going to call this theta 2 because they're 2 different angles. And what I'm going to do is this. I'm going to divide one by the other, like this. I'm going to divide them. When I divide them, because the currents don't change, the currents cancel. Because the magnetic field doesn't change, they can cancel. Because the length doesn't change, they can cancel. The only thing that's left is sine theta 1 over sine theta 2. So F1 over F2, I don't know what those forces are, so I'm just going to leave those as is. I know that the first time, the first angle was 90 because it said perpendicular. A current carrying conductor is placed perpendicular. So the force 1 goes with the sine of 90. The other one is the sine of 30. That's the second angle. So essentially what that means is sine of 90 is 1. The sine of 30 is 0.5. So what I'm going to do is this. I'm going to cross multiply. I'm going to say that 1 times F2 is F2. And then I got F1 times 0.5, or 0.5 F1. So there you go. There's the new force. The new force, F2, equals half of the original force, because the sine of 30 is a half. So whatever the original force was, F2 is going to be half of that. So the answer here is A. Now that was a level 3 question. And once you know how to do it, it seems really simple. Last one on this screen. At what distance from a current carrying wire with 3.5 amps of current will the magnetic field strength be 9.2 times 10 to the negative 3 Tesla? So we use Bio's law. B equals mu I over 2 pi r. But I'm asked to find the distance, which is r. So I need to rearrange that formula. I'm going to say r equals, I can just swap like that, mu I over 2 pi times b. I just swap the r and the b, because that's a property of proportions. You can interchange the top and bottom on opposite sides of the equal sign. So what we've got is this. R equals, mu, remember, is 4 pi times 10 to the power of negative 7. I is the current, which is given, 3.5. Then on the bottom you have 2 pi times b. b is 9.2 times 10 to the power of negative 3. So again, you can cancel 2 pi into 4 pi twice. And when you do that, your distance will work out to be 7.6 times 10 to the negative 5 meters. 7.6 times 10 to the negative 5. That's what you get when you do the calculation. That means the answer is C. Okay, so again, none of these problems are really overly complicated. Let's try some more. This one here. Now this one is a little bit tricky. This is also a level 3 question. Okay, here's another level 3 question. And the level 3 ones, remember, are the ones that are a little different. Probably a unique situation that you may not have seen before. Like this one, for example, you're asked for the magnitude and direction of the magnetic force on the wire when the switch is closed. Well, when this switch is closed, what happens is the current starts to flow in this direction. See that? Current starts to flow like that, because from the battery it always flows from the negative terminal. Let me show you an easy way to do that. The short terminal is always the negative one. Just do this. Draw a little triangle. That arrow shows you the direction of the current. It's a real quick way to do it. Anyhow, when you do that, you need to know the current, because if you want to find the force on a current carrying conductor, first you need to know what the current is. So we use Ohm's law for that. Remember, V equals IR. So I equals V over R. So 12 volts divided by 48 ohms equals 0.25 amps. You got that much. Then, once you know what I is, now you can use this equation, F equals BIL sine theta, plugging in all the numbers you're given. The B is given, 0.082. The current we just found, 0.25. And the length. Now, there's two things given there for length. There's this number and this number. 0.40, 0.25. Now the question is, which one do you use? The 0.25 is the size of the magnetic field, and the actual length of the conductor is 0.4. Now, remember this, that the only part of that conductor that's going to experience a force is the part of the conductor that's actually inside the magnetic field. In other words, only from here to here will you get a force. These other parts that are outside the magnetic field completely will not experience a force. Okay, there's some kind of a shield there that blocks the magnetic field. Just assume that. So the length that we use is actually 0.25 meters. And because it says perpendicular, I've got sine of 90. So I plug all those numbers in, and I get 0.005125, which is 5.1 times 10 to the negative 3. So it's either this one or this one. It's not this one or this one. Now all I got to do is figure out the direction of the force. That's where my left-hand rule comes in, right? Left-hand rule number 3, the motor principle one. Your thumb points in the direction of the current, which is down towards the bottom of the screen. Your fingers point in the direction of the magnetic field, which is into the screen. And if you hold your left hand in that orientation, your palm will point towards the left side of the screen. So that means that the direction of the force is left, and the answer is A. Okay, that's the way you do it. So get used to using those left-hand rules. Like I said, guaranteed you're going to need to use them. So be careful. Let's take a look at the next one. Which occurs when protons and electrons enter a magnetic field that is parallel to their direction of motion? There's the key word right there. Parallel. Now remember, we get the maximum force when it's perpendicular. Then as the angle starts getting less and less, the force gets less and less. When the angle gets down to 0, or in other words, when they are moving parallel to the field, that means there is no force. So if there is no force, nothing is deflected. The answer is actually B. If it was any other angle, anything other than parallel, both would be deflected in opposite directions, but they would both be deflected. There's no such thing as a magnetic field that will deflect only electrons or only protons. The difference is the electrons get deflected one way, protons the other way. But in this one, neither gets deflected because of that word parallel. So you got to read the questions very carefully. And I mean very carefully. Next one, another level 3. This is a level 3. And there are a number of level 3s on your public exam. It's the same number all the time. And I gave you a copy right at the beginning of this whole process, and it's posted there for you to see, a copy of what they call the table of specifications, which will actually tell you how much of your test is level 3 questions. Okay, there is 20% of your test is actually level 3 material. In other words, what's considered to be, it's not really stuff you didn't do before, just stuff that might be a little unique, a little bit different. Anyway, this one here, we want to know the magnitude of the external field. It's a current carrying conductor with that length. So we do this. F equals BIL sine theta. F equals BIL sine theta. Which means if we're trying to find the magnitude of the field, we're going to say B equals F over IL sine theta. So here's what we do. In this one, we're not given the force or the current, but we are given the slope. And the slope is equal to F over I, force divided by current. So we don't know what the force or the current is, but we do know what force divided by current is, because that's the slope. So here's what I do. I'm going to say that's the same thing as saying F over I times 1 over L sine theta. So F over I is 0.23 multiplied by 1 over 2.0 times the sine of 90. And remember, the sine of 90 is 1. So it's really 0.23 times a half, which is 0.115 or 0.12. There's your answer. Okay, so again, a little more complicated, a little bit different. You're not normally asked to do that, but just remember, slope equals rise over run, and on this graph, that happens to be force over current. That happens to be force divided by current. Next one. We got a couple more applications now of the left-hand rule. We got a proton shot through a magnetic field. Now remember, the direction of the magnetic field is always north to south. So there's the direction of your magnetic field. So you're going to use left-hand rule, or if you want, because it's a positive particle, you can use your right hand, like I told you before. So I'm going to use the left hand. Left hand pointing fingers down because the magnetic field is down. Thumb pointing right because the proton is moving right. And if I do that, my palm points out of the screen, out of the page. But remember, this is a proton, so it's got to be the opposite of that, which means it would have to be into the page, because out of the page would be an electron. And this is not an electron, it's a proton. It's the opposite. Okay, now the next one is an electron. So the left-hand rule does work. So the magnetic field this time is coming out of the page, straight out. Your thumb has to point straight down because that's the direction the electron is moving. And if you do that, your palm points to the right of the page, towards the right side of the page or the screen. The reason it says page is because this came straight off an old public exam. So the answer is C. So like I said, get used to using those left-hand rules. Very important. Okay, let's try some questions that are from part 2 of the publics. So here we have a 0.025 meter long wire segment, XY, positioned perpendicular to a magnetic field. So sine of 90, in other words. We want to calculate the magnitude of the force, or sorry, the magnitude of the current and the direction of the current. Okay, so here's what we do. We're going to use F equals BIL sine theta. That's the first thing. Recognize the formula. Then we plug the numbers in. The only thing we don't know here is I. I know the force is given. I know B is given. I know L is given. And I know it's perpendicular, so it's sine of 90. So we do that, we get 11 amps. So there's 11 amps of current. Now, here's the other part of it. I know that the magnetic field lines are going from north to south like this. There's your magnetic field. And it says the force is up. So that force is upwards. There's your force. So if I know the force and I know the field, remember, left-hand rule, motor principle, left-hand rule number 3, your fingers point in the direction of the magnetic field, which is towards the right. Your palm points up because the force is up, and if you do that, your thumb points into the screen. So by using left-hand rule number 3, you get the direction. Okay? The current is actually flowing into the page or from X to Y. Okay? Left-hand rule number 3, that is. So it's a fairly straightforward problem. That's just a standard level 2 question. Let's try the next one. This one asks us for the magnitude and direction of the magnetic field strength at point P. And you can see point P right here. Okay, it's 0.20 meters from wire 1 over here, which means that it's 0.3 meters away from wire 2. We know that because all we got to do is subtract, right? So this distance from here to here is 0.03. So now all we got to do is calculate the two strengths and add them together. And I know I'm going to add them together because, look, I add them instead of subtracting them. And the way you tell that is we look at the magnetic fields for each wire. In wire 1, the current is going upwards. So that means that in the middle, the magnetic field for wire 1 is coming out of the screen because your fingers point out. For wire number 2, it's the same thing because it's wrapping around and your fingers are pointing out on this side as well. They're both outwards, both of them. That's why we add them together. So the overall direction is actually going to be out of the page. Now, if the current was actually flowing in the same direction in each, the same direction, that would mean you'd have to subtract them because they'd be in opposite directions. Okay, the magnetic fields would be in opposite directions. Anyway, moving on, we add the two field strengths together, so it's mu I over 2 pi r for both. Fill in your numbers. Right, again, you can cancel out your pi's, and your 2 can go divide up there as well. Right, and then once you do that, you get 3.0 times 10 to the negative 6 plus 3.3 times 10 to the negative 6, which gives you 6.3 times 10 to the negative 6 Tesla. And because both fields are out of the page, then the overall, or the net field, is also out of the page. All right? That's the way it works. Next question. This time we have a 75 ohm resistor that is 0.28 meters long, is placed in a uniform magnetic field, and the resistor experiences a force of. This time it says, calculate the voltage across the resistor. Well, that's another level 3 question, but we just did one in the multiple choice very similar to that. What we're going to do is we're going to find the current first. We find the current first using F equals BIL sine theta, because we know the force, we know the field strength, we know the length of the resistor, and we know the angle is 90 degrees because it's perpendicular to the magnetic field. It tells us that in the question. So we do that, we find I. I equals 0.57 amps. Now that we know I, and we know the resistance, it's just a matter of using Ohm's law, V equals I times R. So we take the current that we just found, multiply it by the 75 ohm resistance, and we got a voltage of 43 volts. Okay, so level 3 again, and it's level 3 because it's kind of a combination of two topics. Two things that you've done before, but not necessarily in the same question. That's what makes it level 3. Like I said, there's nothing there that really you haven't done before. It's just you may not have done both of those things together before. You've done them both separately, just not together. All right, next one. This time we need to calculate I1 so that the net magnetic field is 0. Net magnetic field right there at point P, 0. That means that the two fields have to be equal in magnitude but opposite in direction. So in other words, field 1 has to equal field 2. Now we're given enough information to find field 2 because B2 equals mu I over 2 pi r. So that's the first thing we do. We find field 2. There it is. There's the field strength for number 2, wire number 2 at point P. So in other words, the field strength for wire number 1 at point P has to be exactly the same, which means, and we got to find the distance too. Remember, the total distance was decimal 020. The distance to the other wire was 0.0050, so you subtract, you get 0.015. The two fields are equal, so there's what you calculate. You plug the numbers in, there's what we get for the current. Right? We know the field strength because it was equal to the other one right here. Right? Those two have to be equal. And then you just plug everything else in. The only thing you don't know is the current. That's it. So again, not an overly difficult question, but sometimes that type of thing does show up. Another one. This one says an electron is projected perpendicularly into a magnetic field and travels in a circle. Now, as soon as you see the word circle, you should be thinking centripetal force. Centripetal force. So in other words, the force acting on that electron because of the magnetic field, or in other words, the magnetic force, is going to be equal to the centripetal force. Okay, that's another pretty standard question. So the magnetic force equals Fc. So in other words, QVB sine theta equals mv squared over r. That's it. Again, that's kind of a level 3 question because it's taking two things that were in different places in the course and putting them together in the same question. So that's kind of a level 3 again. Plug in the numbers. The only thing we don't know is the v. So we got a v here and a v squared over here. When we have that, what we can really do is we can cancel out, whoops, we can cancel out this v and one of these v's. So we get rid of the v squared and we just got a v now on one side. And if you do that, here's what you get. Okay, which means that, and when you solve, you get 4.0 times 10 to the 7 meters per second. Done. And that's all there is to these. The only thing that makes that one a little more challenging is the fact that because it's traveling in a circle, you have to remember to use centripetal force. Centripetal force. Okay, one last question before we end, because I know this is starting to get a little long, but a 0.16 kilogram metal rod is in a horizontal magnetic field. So the current is going through the rod. So here we go. Negative terminal is down here. Here's the negative terminal right here, which means that my current leaves there, comes up the rod, across here, down here, and back to the battery. So as it goes through here, it creates a magnetic field. Now, the current that must flow through the rod in order for it to remain at rest. In other words, we need enough current going through that rod to give us enough magnetic force to overcome the force of gravity. We need to overcome the force of gravity. So here's what we do. We say that the magnetic force is equal to the force of gravity instead of centripetal force, right? It's almost exactly the same thing, which means that BIL sine theta, because this is not a single charge this time, this is a current going through a conductor, BIL sine theta equals mg. Plug in your numbers, right? I equals mg over BL sine theta. Plug in your numbers, and it's sine 90 because that is going perpendicular to the magnetic field. You can see that, right? There's a right angle right here between the current and the magnetic field. So there is a right angle, 90 degrees. So that gives us this answer. 26 amps is what we need to keep that rod suspended at rest. In other words, to make the magnetic force exactly equal to the gravitational force. And that takes us to the end of this section. What we're going to do in our next lesson is we're going to take a look at electromagnetic induction. Again, it's a link between magnetic fields and electricity. Because if we can create a force by the interaction between two magnetic fields, then it makes sense that if we exert a force and move something through a magnetic field, maybe we can actually create a current too. And that's what the next topic is going to deal with. So again, study hard. Make sure you're prepared for your exam, and I hope this stuff is helping you along in the way. And good luck.